in this example, we have 24 slots. So we have 24 slots. We have 4 poles and 3 phases. So that gives 2 slots per pole per phase. And so we did this before we did something similar like this before with 2 poles. So when we had 2 poles, we had 12 slots, which gave 2 slots per pole per phase. So in this example here, what I've tried to show one set here of windings. So this is these windings here are chorted by 1 slot. You can see the top is shifted to the left by 1 slot. So there's 1 slot chorting. And so what I've done here is I've added in the how the winding could be connected. Yeah, this should go from the bottom one out. So usually with the windings, they go from bottom slot to top slot, or from top slot to bottom slot. So this one comes from the bottom slot over to the top slot. Then this is going through the machine. Then it comes out the back, and then comes back around to slot number 2. And then it comes out, and I did the same. I did the same thing, and this one comes out. So this one comes out and back here, and then this one comes out and back like that. So it's top to bottom. Now the question is, so then we would then we'd go round, and so we've got the 4 coils going in here. So then we'd go round to the next set. So there's 4 poles here. So we have to have 4 phase groups. So this set of 2 coils here is called a phase group. So another name. So we've been saying that this is 2 slots per pole per phase. Another name for this is a phase group of 2. So then this is we've used Q as 2 for slots per pole per phase. We can this would also be NP equals to 2, because the phase group has one chorting on it. So in our equation. Now now if we look at the next winding, then this would come out of slot 12 and then go around, say to slot 7, like that. And then we've got this one here is on the top. This would come out. This could come out and go around like that. And then these two coils have to be connected. And so then one option is that this would come through the back and connect like that. So that would all be in series. So this set of windings here will create, if you look at the right hand rule, then you'd be creating a south pole here, and then this here is going to be creating a north, and then this will be creating a south and then a north if you go around. So the question is, though, we have a number of options in how we connect up these phase groups, these sets of coils associated with a particular phase. This would be for, say, phase A winding. So the way that we connect up each of these phase groups will result in a different voltage being created. If we were creating rotating magnets around, then we would get a different induced voltage depending on how we connected up these phase groups. So there's really three options when we connect up the windings. Any questions on that? So the purpose of this was really to, the purpose of this example is actually just to talk about this being a phase group. So you've got 4 poles, and this would be considered one phase group which has 2 coils. But I wanted to show this example to help illustrate my next point, which is how these groups of windings could be connected up and how that affects the voltage, induced voltage, if it's a generator. So 6.5 winding connection. So in that example, we considered a phase winding for a 4-pole 3-phase stator. So one phase group, we would have 4 phase groups in that example. One phase group could be represented like this, where the dot represents the direction of the induced voltage. Dot denotes polarity of induced EMF at one instant of time. So we really have 3 options. We have series, parallel, or series and parallel for the windings. So series connection, and I'm drawing this in a way to confuse you, because I probably haven't confused you enough. So the reason I was drawing it like this is to show that this part is going around the back. And it's going to be creating. So the first in the example, one's going to create a north and one's going to create a south. One phase group is going to create a north pole. One phase group is going to create a south pole. So in order for you to create opposite voltages, opposite poles, the direction of the current has to be going the opposite way. But that doesn't mean that the voltage has to. The voltage still needs to add up. And so the net voltage would be 4 times each individual one if it's in series. And then the other option is parallel. I can call these, I'm going to give them names to keep them the same on each of these three drawings. So we can put them in parallel. Like so. So then the back EMF voltage, the induced voltage, would be equal to the individual voltage on one phase group, and then surprise, surprise, the third is series and parallel. So this would, and this would be A1, A3, A2, A4. Again, so the A1 would be creating north, A3 south. Sorry, A1 and A3 would both be creating north. A2 and A4 would both be creating south poles. So then in this case, it's going to be 2 times E RMS. So the upshot of this is that the voltage that you're going to get at the terminals is going to be a function of how many are in parallel, because in this when this is in series, we're going to get 4 times. So we can, and then in this one you're going to just get the 1, right? So then in general, phase voltage for a generator with P poles and A parallel paths is equal to EA times P over A times E RMS. Proportional. So then with this then we can further modify the we can further modify the voltage. So we calculate the ERMS with the distribution and the pitch factor. Now if we have the windings in parallel, we're going to divide it by the number of parallel paths, and we can put the poles in there. So okay, now there's two other factors to consider. If we now think about the fact that the slots are not just like a delta function change, or a step function change, I should say. if we actually think about the slot a little bit more, then this slot is likely going to be filled up with lots of coils. So we can model that more accurately without too much work, actually. So this could have N windings. So then if we were to draw up the winding and turns function, in this case, the turns function is shown here. So if we, starting from at this point, there's no, again, the turns function tells you the physical location of the windings. So if we're moving along from starting, we get to the edge here, now we're going to start to see all of these coils. So rather than, so previously we just assumed a straight step change. Now if we could model it, we could do multiple little step changes, like that, but that would be rather a pain. That's getting maybe just too much. But we can make a better approximation of what's going on by assuming that the turns function doesn't go straight up, but goes on a continuous increase, linearly increasing, and then when we move across here, and then it linearly decreases, like that. So then we could define the middle point as the 0. Then this half of this is going to be x over 2. X over 2, like that. So that's the turns function. The winding function, we take the average of the turns function, and minus it from the turns function. And so when we do that, we're going to get out a waveform that I will try not to mess up. That looks something like this. So it's not entirely a square wave anymore. So then the question is, and then this point here would be 0, and then this point here would be x over 2, where x is the whole slot width. So then we can calculate the Fourier series of this and find out what the factor is that we could then just multiply our winding function by. So for the Fourier series, with this waveform, the DC component is 0, and we can use quarter wave symmetry. So it's it looks like if we start this as 0, then it's an odd function. So from our definitions that we had before, the even function term is 0, and it has quarter wave symmetry, so that we have only odd terms with quarter wave symmetry. So then the Fourier series term I need these to be evaluated from 0 to pi over 2. This is pi over 2 here. So from 0 to x over 2 we have a linearly increasing function. So this is n theta. So we have n theta sine n theta d theta, like that. Okay, so we can now separate that. So we've got two parts. We've got from 0 to x over 2, and then from x over 2 to pi over 2. So we have we can take out the magnitude nw, and then we're going to integrate from 0 to x over 2. And so when theta is equal to x over 2, we need it to equal nw. So this will do that. Could I put the nw outside? Sine n theta. I feel more awake after the break. X over 2 pi over 2 sine n theta. Okay. Maybe I shouldn't have said. Maybe I spoke too soon. Okay, so now we need to evaluate that. This is a little bit tricky. This one, it's with the theta in front. I'm just going to give out the answer here. So we, and you can check it. It's only takes a minute to check. So I've taken the x outside here, and so we have sine n theta divided by n squared minus theta cosine n theta divided by n plus the integral of sine is minus cosine pi over 2 to x over 2. Okay, so when we put in the, if I have my cheat sheet, we put in the values. We get Bn is equal to 8 Nw pi x sine nx over 2 divided by n squared minus x cosine nx over 2 divided by 2n minus 4 nw divided by pi n. You can check that, by differentiating it. When you differentiate the second term, you'll get a cosine here. When you differentiate this, you get a cosine. So then that term cancels out, and then you're just left with the theta sine term. And then the second part is pretty straightforward. So this term is going to be 0 always because n is odd. And this is x here. There's an x on the bottom here. They cancel. There's a 2 here. That becomes 4. This, if you look at this, is the same as this term, but this is a minus. Minus minus gives a plus. These two terms cancel, and you're left with Bn is equal to 4 NW I'm putting a 4 here. I'm going to stick a 2 on the denominator. Pi n times sine nx over 2 divided by nx over 2, like that. So in this form, we've got it in this. We've got the 4 nw over pi, which we were using before. So then we can write out. So remember, this is for n equals odd. So then we can put this Fourier term back into the winding function, and we get out 4 nw pi n times sine nx over 2 divided by nx over 2 times sine n theta. And n is odd. Now if we compare that to the 1 slot per pole per phase, this for 6 slots, where the pole pitch and the coil pitch are the same, i.e. the square wave, then we had 4 nw divided by pi n sine n theta. So comparing these two, we can remember that why I'm comparing these two is this one is if we ignore this effect and we have a square wave instead. So how does this affect the voltage? This will give it to us. So we take the ratio of the two. So we have taking ratio, we have, I think you can see that everything's going to cancel except the part in this brackets here. So we can then define a slot opening factor as the difference which is sine nx over 2 divided by nx over 2, where x is the slot opening size. Any questions? Does that make sense? Okay, so last but not least, well maybe least, yeah, probably is least, but last and least, we can account for one additional thing that can make the machine do something that we didn't expect. We could have a look at skewing. I don't like skewing. I think it's kind of cheating. But some induction machines are skewed to reduce torque ripple, and it's quite expensive if you want to do it with the stator. But it actually is a very quick calculation. So now think about the right. Okay, well, I'm going to draw this in two views: radial view and axial view. So radial view is you're standing on the rotor, you know, as you did with the electric machines class, looking up, or you could look down, I suppose. And then you would see that the winding where this is the axial direction doesn't go straight across, but goes on an angle. So this would be the axial width. And so we have something that looks like that. So this would be, say, the current going out, and this would be the current going in. Maybe this, and so that's radial. Maybe that's not clear. So maybe I can try to draw it like this. So this is the machine. It could be the rotor or the stator, which have the winding. Now, and then that dotted line would be directly going axially across, right? So then the winding would be, instead, have a skew. So instead of the slot effectively shifts as you go along. You can look, if you type into Google skewed stator, you'd see this. And so then, now one way to model that would be to try to do a three-dimensional finite element analysis. So I'll leave that as a homework. No, I don't think I won't do that, because I don't think the program can, the student version can do that. So, but I'll leave that as a extra bonus exercise to do. So the question is, how would that affect the winding? And luckily we've already derived the answer. So if you think about it, if you're looking in this way, and then if you're looking in axially, and then you're at this location, and then you start to maybe you're still, right? But this moves. Then what you would see is the winding would keep coming into view, because it wouldn't just be at one point. As you go around, you would still see part of the winding. You'd be, if you're at this point here, you're still going to see, assuming you could look through the metal, you're still going to see some of the winding. So therefore, how we could model that is just like what we did here. So the turns function would then look like this, where I'm defining this as alpha, not gamma. And so then we have the same winding function. So the one we derived before, we can use the same thing, we just put different values in. So then if there is skew, we could model that by using a skew factor. So winding skew factor, which is sine n alpha over 2 divided by n alpha over 2, where n is the harmonic. Okay, is that reasonable? So then now we can put all of this together. So we have a total winding factor. So the total winding factor is defined as Kn, which has got the, and now I'm adding a harmonic here. We just did the fundamental, but if you really want to be nihilistic, you could calculate for other additional harmonic terms. Pitch. So n is the harmonic. So we have the pitch factor, we have the distribution factor, we have the slot opening factor, and we have the skew factor. So pitch factor, the distribution factor, maybe this one should be called the X factor, the slot opening factor, and this one's the skew factor. So all of these go in, and then in addition to that, we have the when we're calculating the voltage, we need to account for if the winding is how the winding is connected, if it's series or parallel, or series parallel. So so the total winding factor is defined as where we have that the winding function could be written neatly as Kn sine n theta, where n is odd. So we don't have to worry about even. So that Kn as now, if you see that Kn now, you can realize that there could be a lot that goes into that number there. And so then the induced voltage in the machine due to nth harmonic is going to be P over A times that ERMS, where we can write it as 2 pi f divided by square root of 2 n times the whoops, that should be NW there, right? Yeah, that's NW. NW flux times Kn. Okay?